For almost a century, we believed we were getting closer to the full picture of the universe. Not every detail, of course. There were still mysteries. Dark matter, dark energy, the usual unknowns. But the overall framework? That felt solid. The universe began with the Big Bang. It expanded. Galaxies formed. Stars lived and died. And over time, science built a model that could explain all of it with astonishing precision. It wasn't perfect, but it worked. Then James Webb started looking deeper, and instead of confirming what we thought we knew, it exposed something much more unsettling. Because right now, the most advanced observations ever made are pointing to a possibility that sounds almost absurd. What if our model of the universe is missing something fundamental? What if one of the most important numbers in cosmology is wrong? That may not sound dramatic at first. Just a number. Just a tiny mismatch between two sets of measurements. But this is the kind of mismatch that can change everything. The age of the universe, the rate of cosmic expansion, the timeline of the first stars and galaxies, even the story of how everything we see today came to exist. And the strangest part is this. Scientists didn't expect James Webb to make the problem worse. They expected it to solve it. Instead, Webb may have confirmed that the crisis is real. Because the deeper we look into the universe, the less certain our cosmic map begins to feel. And this is what makes the moment so fascinating. This is not the story of a failed theory. It's the story of a model that still explains an enormous amount, but may no longer explain enough. A model that works beautifully until you look closely at the cracks. So in this video, we're going to unpack the growing crisis in cosmology, the strange conflict over how fast the universe is expanding, and why James Webb may be forcing scientists to confront a possibility they've tried to avoid for years, that we may have misunderstood the universe itself. At the center of this entire story is a number that sounds almost too simple to cause this much trouble. It's called the Hubble Constant, and all it's supposed to tell us is how fast the universe is expanding right now. That's it. Not how fast it expanded billions of years ago, not how fast it might expand trillions of years from now. Right now. You would think that by this point, with all the technology we have, this would be one of the easiest numbers in cosmology to pin down. But it isn't. And the reason this number matters so much is because cosmic expansion is not just some background detail. It affects almost everything. If the universe is expanding at one rate, then it has one age. If it's expanding at a different rate, then that age changes. The distances between galaxies change. The scale of the observable universe changes. The timeline for when the first stars formed changes. The timeline for when galaxies assembled changes. A single number ends up shaping the history of everything. To understand why, imagine drawing a map of a country. If your scale is even slightly wrong, then every road, every border, every distance on that map becomes distorted. Now imagine doing that, not for a country, but for the entire universe. That's what the Hubble Constant does. It sets the scale of the cosmic map. And the weird part is, this number has been controversial for a very long time. Even back in the early days of modern astronomy, scientists struggled to agree on how fast the universe was actually expanding. For decades, the estimates were all over the place. The numbers kept changing. The uncertainty was huge. But over time, the measurements improved. Telescopes got better, methods became more refined, and eventually, it looked like the chaos was over. By the early 2000s, cosmologists felt like they had finally cornered the answer. The values seemed to settle into a narrow range. The field moved forward. The problem looked basically solved. But then something unexpected happened. The better our instruments became, the more the disagreement came back. Not as a huge, obvious error, not as some embarrassing mistake anyone could spot immediately, but as a stubborn, precise, deeply uncomfortable mismatch. And this is what makes it so dangerous. Because when science improves, the uncertainty is supposed to shrink around the truth. Instead, in this case, the uncertainty shrank and revealed two different answers. Not one, two. Two values for the same universe. Two measurements that should agree. Two versions of cosmic history that do not line up. And once that happened, the Hubble constant stopped being just another number. It became a warning sign. Because if we cannot agree on something this fundamental, something as basic as how fast the universe is expanding, then the problem may not be in the measurement alone. It may be in the model underneath it. And to see why this became such a serious crisis, we need to look at the two different ways scientists are measuring the universe in the first place. Because both methods seem to work, and that is exactly the problem. The real reason this became a crisis is simple. Scientists have two different ways to measure the expansion of the universe, and both give different answers. The first method looks at the early universe. It studies the cosmic microwave background, the oldest light we can see, and uses the standard model to calculate how fast the universe should be expanding today. That method gives a value of about 67. The second method looks at the present universe. It measures distances to stars and exploding supernovae in nearby and distant galaxies, then uses those distances to calculate how fast space is expanding right now. That method gives a value closer to 73. And that is the problem. These are not rough guesses. These are two serious methods built on decades of data, and they should agree, but they don't. One points to a slower universe, the other points to a faster one. And once that happened, the question stopped being, which number is right? It became, why does the universe seem to be giving us two different answers? At first, the difference doesn't sound dramatic. 67 versus 73. That barely sounds worth arguing over. But in cosmology, this is not a minor disagreement. This is the kind of gap that can shake the entire timeline of the universe. Because the Hubble constant is not just one number sitting alone on a chart. It controls the scale of everything. If the universe is expanding faster than we thought, then it may be younger than we thought. The distances between galaxies shift. The timeline for when the first stars formed shifts. The timeline for when galaxies grew and evolved shifts too. In other words, you are not changing one measurement. You are changing the story. And that is why this became so serious so quickly. If the two methods were only slightly imprecise, scientists could shrug and wait for better data. But that is not the situation. These measurements are already extremely precise. So now the gap feels less like noise and more like a warning. A sign that something in our cosmic model may be missing. And for a while, that still did not mean a crisis. Because many astronomers believed the explanation was probably simple. Maybe one of the methods had a hidden flaw. Maybe one telescope had introduced a subtle bias. Maybe the distance measurements were being thrown off by messy, crowded regions of stars. That was the hope. Find the error, fix the error, and the tension disappears. And that is exactly why so many people were waiting for James Webb. Because Webb was supposed to be the telescope that finally settled the argument. Not by giving us a new mystery, but by cleaning up the old one. Before James Webb, one of the biggest suspects was simple. Bad distance measurements. Not because scientists were careless, but because space is messy. Some of the stars used to measure distance sit inside crowded, dusty regions of galaxies. And when older telescopes looked at them, nearby starlight could blur together, making those stars appear brighter than they really were. And if a star looks brighter than it should, it can trick you into thinking it's closer than it really is. That may sound small, but across cosmic distances, small errors grow fast. So the idea was straightforward. Maybe the high expansion rate was not real. Maybe it was just a measurement illusion caused by limited resolution. And that is exactly why James Webb mattered so much. Webb can see with far greater clarity, especially in infrared, which helps it cut through dust and separate details older telescopes could miss. In other words, if the problem came from blurry, crowded data, Webb should have exposed it. That was the expectation. A sharper telescope, cleaner measurements, crisis over. But that is not what happened. When Webb looked at the same kinds of stars, The numbers did not fall back into place. They stayed high. And that was the moment this stopped looking like a technical glitch and started looking like something much more serious. This was supposed to be the fix. Instead, it became the confirmation. When James Webb rechecked the key distance measurements, many scientists expected the higher value to drop. They expected the tension to soften. They expected the two methods to finally move closer together. But Webb did not rescue the standard picture. It backed up the earlier results. The same stars still pointed to the same distances. The same ladder still pointed to the same conclusion. And the faster expansion rate did not disappear. That changed the tone of the entire debate, because once the measurement error starts getting ruled out, the question becomes much harder to avoid. What if the problem is not the telescope? What if the problem is not the stars? What if the problem is the model itself? And that is why this became more than just a disagreement between teams. It became a real cosmological crisis. Because now, scientists are left with two possibilities. Either there is still some hidden error nobody has found yet, or the universe is doing something our current model does not know how to describe. And once you get to that point, you are no longer just refining a theory. You are testing whether the theory is missing part of reality. Once Webb confirmed the higher expansion rate, cosmologists had to consider a much more uncomfortable idea. Maybe the universe changed in a way our model never included. One of the biggest ideas is something called early dark energy. The basic concept is simple. At some point shortly after the Big Bang, the universe may have gone through a brief extra burst of expansion, a kind of temporary push that later disappeared. If that happened, it could help explain why the early universe predicts one number, while the present universe gives us another. The important thing is this: scientists are not talking about throwing away all of cosmology. They are trying to figure out whether one missing ingredient could repair the gap. But so far, that ingredient has not been proven, and that keeps the mystery alive. Because right now, early dark energy is still just an idea, a possible fix, not a confirmed discovery. And before that mystery could even settle in, James Webb opened another one. Because it wasn't just the expansion rate that started looking strange. It was the early universe itself. As if the expansion problem was not enough, James Webb found something else that made scientists uneasy. It started seeing galaxies in the early universe that looked far more developed than expected. Not tiny primitive systems just beginning to form, but surprisingly massive galaxies, showing up only a few 100 million years after the Big Bang. That is a problem, because building a large galaxy is supposed to take time. Stars have to form, matter has to gather. Galaxies have to grow through mergers and gradual evolution. But some of Webb's early observations seem to suggest that parts of the universe grew up much faster than they were supposed to. Almost like the early cosmos skipped steps. For a moment, this raised a huge possibility. Maybe the standard model was not just struggling with expansion. Maybe it was also underestimating how quickly structure formed after the Big Bang. And if both of those things were true at once, then the cracks in cosmology were starting to connect. To be fair, not every shocking galaxy turned out to be a disaster for cosmology. Some of the earliest impossible galaxies were later re-examined, and astronomers found that active black holes may have made them look brighter, and therefore more massive than they really were. In other words, some of these galaxies were not actually packed with that many stars. They just looked that way because the material falling into their central black holes was producing enormous amounts of light. That helped. It removed some of the most extreme cases, but it did not make the tension vanish. Even after those corrections, the early universe still seemed to contain more large, evolved galaxies than expected. So the situation became more nuanced. Not a total collapse of the model, but not a clean victory for it either. The standard model survived,
but it did not come out untouched. And that is what makes this so interesting.
Because in science, the biggest breakthroughs do not always begin with a theory completely failing. Sometimes they begin when a theory keeps working. And that is where the story stands right now. The standard model of cosmology is not dead. It still explains an incredible amount. The early universe, the cosmic microwave background, the large-scale structure of space. That is why this situation is so unusual. Scientists are not dealing with a theory that failed overnight. They are dealing with a theory that still works extremely well, but keeps running into problems it cannot fully explain. The expansion rate does not line up cleanly. The early universe looks more complicated than expected. And even dark matter and dark energy, the ingredients that make up most of the cosmos, are still deeply mysterious. So this is not the collapse of cosmology. It is something more subtle, a model that still stands, but under pressure. And when a model this successful starts showing multiple cracks at once, scientists pay attention. Because sometimes that is how a scientific revolution begins. This is why so many scientists are taking the situation seriously. Not because cosmology has failed, but because this may be one of those moments when science reaches the edge of its current map. History has seen this before. A theory works for years. It explains almost everything. Then, better instruments arrive, better data comes in, and suddenly the old picture starts to feel incomplete. That does not mean the science was wrong. It means it was unfinished. And that may be exactly where we are now. James Webb has not destroyed our understanding of the universe, but it may be revealing that the universe is stranger than the version we have been using, and that is what makes this moment so exciting. Because if these tensions are real, then the next breakthrough in cosmology may not be a small correction. It may be a whole new layer of reality we have not understood yet. So no, James Webb has not proven that our model of the universe is wrong. But it may be showing us that the model is incomplete. And that difference matters. Because the biggest breakthroughs in science usually do not begin when everything falls apart. They begin when reality starts refusing to fit the picture we thought was finished. Right now, that may be exactly what is happening. A small gap in the expansion rate. Strange galaxies appearing too early. A universe that still follows the rules, but not as neatly as it should. And maybe that is the real story here. Not that cosmology is broken, but that we may be standing at the edge of its next revolution. Because if the universe is trying to tell us something, James Webb may be the telescope that finally forced us to listen.